Hello everyone. Today we are looking at electricity. So we are going to start with since last time we looked at static electricity, so now we are moving on to electricity when you're looking at circuits. So we'll start with electric current. So we are saying electric current is the continuous flow of charges relatively for a long period of time. So we are saying, if you remember, we spoke about electric charges when you're looking at charges, right? So now we are saying electric current, which is represented using I, we are saying is the flow of charges, right? Is the flow of charges. But if you are given a conductor, if you have your conductor, let's say it's a conducting material, right? And then this conductor, of course, has electric charges. And if it's a conducting material, it has delocalized electrons. Delocalized electrons, right? These are mobile electrons which can freely move within the conductor, isn't it? So now we are saying these electrons, which are the charges, these electrons can move from one point to another within the conductor, but something has to be done for the electrons to move from one point to another. At this point, whereby we are saying we are taking a conductor, whereby we have an isolated conductor. We have an isolated conductor, right? We are saying within this isolated conductor, we have moving charges, right, which are the electrons. We are saying the electrons within an isolated conductor, they are moving the electrons within the isolated conductor. Within the isolated conductor are moving randomly. They are moving randomly. Okay, we are saying this is just an isolated conductor that is not conducted to anything. So the electrons within this conductor are moving randomly, isn't it? With an average drift speed. So now we are saying if we apply a potential difference between the two ends of the conductor, then the electrons will move from one point to another in the same direction, because we are saying if they are moving randomly, they're moving in different directions, right? So now if you apply a potential difference between the ends of the conductor, then the electrons will move in one direction with the same speed, right? So now we are saying when we apply a potential difference, which I'm going to represent as potential difference PD, potential difference across the ends of a conductor, what happens? So we are saying if we apply a potential difference across the ends of a conductor, we are saying first of all the electrons within the conductor, they will move in the same direction, with an average velocity. So now we are saying when you apply the potential difference between the ends of the conductor, another thing is being set up within the conductor. An electric electric field density or electric field strength is produced, which is being set up between the ends of the conductor. So now, if there's an electric field within the conductor, that means there's an electric force because remember, this is a distribution of electric charges, isn't it, that are in motion, which means when there's an electric field within the conductor, there's also an electric force between the charges. In our case, our charges, we are looking at electrons. So now I want you guys to understand something. The flow of electrons, since the electrons are moving and they are close to each other, the flow of electrons will create an electric force on the electrons, and hence an electric current is produced. So now we are saying, if we have our conductor, we come back to our conductor again. For now, we are saying if we have our conductor and then we apply a potential difference between the ends of the conductor. Now the electrons will move in one direction. Instead of moving randomly, they'll be moving in one direction. So what is the direction of those electrons? We are saying if we have a potential difference that is applied within the conductor, the electrons will move from the negative terminal to the positive terminal. They are moving from the negative to the positive terminal. So the movement of these electrons from the negative to the positive terminal, it creates or induces current. So we are saying currents will move in the opposite direction of the electrons. So currents will move from the positive terminal to the negative terminal. To the negative terminal of the applied potential difference. So now we are looking at firstly we are looking at an isolated conductor, right? Whereby we said the electrons within the conductor, they are moving randomly in different directions. So now, and as they are moving randomly in different directions, they are colliding with atoms, right? So now, when you apply PT across the ends of the conductor, now the electrons will move in one direction, right? They will move in one direction within the conductor with an average velocity, isn't it? So the movement of these charges, which are the electrons, the movement of these charges, they will move from a negative to a positive terminal, which means they are moving in the opposite direction as current. So we call this convectional current. Convectional current is the flow of charges, right? Conventional current, which means it moves from positive to negative, right? It moves from positive to negative, which means we can say that the conventional current is the flow of positive charges, right? Because if you have positive charges within this conductor, positive charges, they will move from the positive terminal to the negative terminal, right? So we can say, which means current moves in the same direction as positive charges, right? Because we are saying if electrons are moving from the negative terminal to the positive terminal, remember this is our terminal, negative, positive, and we applied this to our conductor. This is our conductor, right? So this is the negative terminal, which means our electrons will move in this direction, right? This is the direction of our electrons, and then this is the direction of our current. This is the direction of our current, right? So in order for current to be induced within a conductor, we are saying electrons have to flow within that conductor, right, in the same direction. And how can that happen? If we apply what? If we apply a potential difference, if we apply a PT across the ends. But we do have conductors whereby you don't necessarily have to apply a PT across the ends. The current will just move. We call those superconductors, but we're going to talk about them later. So now we are saying we have this, right? So we said, remember we said what is current? Current is the flow of charges within the conductor. It's the flow of charges. So now we can actually define current in a more scientific way. So current is the flow of charges, isn't it? Which means charges are flowing with respect to time, right? So now we can say current is the rate of flow of charges, right? It's the rate of flow of charges through a point within a conductor. Through a point within a conductor. So now, which means we can write an equation, we can generate an equation for current. We're saying current is equal to the rate of flow of charges, which means the rate of flow of charges, which means it's going to be current is equal to charge over time, because it's the rate of flow, which means the quantity of charges divided by time. So this is the first equation that is very important that you guys have to know. Current is equal to charge over time, the rate of flow of charges. And normally in most textbooks, they represent it like this. In most textbooks, they represent it like this. Q is equal to IT, which is still the same thing. We just made Q the subject of the formula, which means charge is the product of current times what times time. And we are saying current is measured, the SI unit for current is the amp, represented